Okay, building on our last lecture with stability, which is the basic idea that as your trials get larger and larger and larger, things get more and more stable, right? Think again, Vegas. You might have peaks and valleys. Somebody wins big one night, or a whole bunch of people lose big one night. But on average, that all sort of evens out. Things become more stable over time. And what does that stability show? The house wins on average. You don't. It's not in your favor. Normal approximations now are basically talking about in greater detail what that notion of stability amounts to. So you have what are called normal curves or bell curves and how they relate to sample. Okay? Bell curves are called normal or sometimes Gaussian. Gauss is the guy who came up with this. He did many things. Einstein's considered a genius. This guy's greater. I mean, the stuff he's contributed to mathematics and other things is just phenomenal. You can look at him up. Johann Gauss, I think. Uh, there are two kinds of other curves. They're called bimodal, which looks like two humps on the camel. Bi for two modal, two modalities, two humps on the camel. They might measure things like, say, average heights of males and females across the world. On average, males tend to be taller than females. So you're going to get not one hump, but two separate humps. The bell curves we focus on just have one hump. They're not bimodal. Okay. So terminology building upon what we covered last time. The sample mean is denoted by the capital letter X. The sample standard deviation is denoted by this SD. Okay, and it relates to the ideal. Remember our sample, tossing the coin 20 times for a class of 100. You're going to get a sample result. So in that sample of a class of 100, you're going to get a sample mean number of heads and a standard deviation. The sample mean is just the average number of heads that we have, and then the sample standard deviation is just how spread out are these results. Do we get a lot of heads? Are they cluster close together? Are they all over the place? What? Ideal mean is the ideal, and that's called this mu. It's basically a Greek letter. It's read mu for mean, mean, right? Uh-huh. Ideal standard deviation is this thing right here, this O thing. This is the Greek letter for sigma, okay? For sigma, basically standard deviation, sigma. From Bernoulli's theorem, remember, we expect that as the number of trials increases, the closer our sample moves to the ideal, right? So that means not just for the average, but also for the deviation. The sample standard deviation moves closer to the ideal standard deviation. For any particular sample with its own mean and its own sample standard deviation, they may differ quite a bit from mu and sigma. Yeah? One way in which this is talked about is the notion of regression to the mean. So you might find, say, just out of pure chance, pure luck, somebody one night has a really hot scoring night, even if they're not like a superstar in the team. You might say they're a pretty good player, but they get hot that night. What's the tendency after that night when they get really hot? Well, the next night they're going to not shoot as well. And people say, oh, he's tired, he's fatigued, oh, blah, blah, blah. No, it's just statistically, it's regression, what's called regression to the mean. You go back to your average. Your average means some days you're going to be really good, other days you're going to be really crappy. But on average, you're going to be here, right? So if you got a really good night, the next night, chances are you're going to be closer to the middle. Not that you're off or you're cold, it's a regression to the mean. So again, any particular sample, like a particular performance where you're hot, or a particular performance where this athlete is cold, may be quite far from the ideal, the average. Okay, tossing a coin gives us what's called a binomial. This is different from bimodal, a binomial distribution. Binomial theorem, for those who remember from high school math, Pascal came up with that. If you don't have any idea what I'm talking about, don't worry. It just means there's two, right? Heads or tails, that's the bi part, and the binomial has to do with one. It's represented the way in which it's going to be represented in terms of a bell curve. And again, the idea is that when you toss points in your sample, the graph of your chart results in getting a binomial distribution that approximates the Bell / normal / Gaussian curve. What? Okay, let's cover some more terminology first. These two things you need to know. Remember, things in red you have to memorize. Mu, the ideal mean, equals p times n. Sigma, the ideal standard deviation, equals the square root of 1 minus p quantity times P times N. Okay? So if you got 100 tosses, the ideal is 50% times 100, 50 hits, exactly. And the sample standard deviation would be 1 minus 50% times P, 50% times N, the number of tosses, 100. So that would be 1 minus 50, which is 50% times 50%, which is what? 5 times 5 is 25, but you got to move your decimals. It's 0.5 times 0.5, right? So 25, how many decimal places do you move it? Well, 2, because there's 1 for each, so you move it 2. It's 0.25 times 100, which is going to give you that. Or if you like, it's 1/2 times 1/2 times 100, so it's 1/4 into 100, which is 25. Square root of 25 is plus or minus 5. Remember, plus 5, it's 5 times 5, or minus 5 times minus 5, each equals 25. When you take the square root, there's going to be two sides. And the idea there is, why do you need that? Well, from the mean, mu, which is in this case 50, it's going to be plus 5 or minus 5. So 45, 50 minus 5 is 45, and 50 plus 5 is 55. And you're saying the standard deviation on average would deviate from 50 plus or minus 5 hits. Okay, our sample, recall from the last lecture, looks something like this. But the idea is, as you increase those trials, these infelicities, these bumps, tend to smooth out. Things get more stable. What does the ideal stable distribution look like? It looks like that. That's what a bell curve is. It's basically these trials repeated to infinity so that eventually it gets smoother. Instead of this, you get more lines in between, and the lines fill in more and more, and they get smoother, and it looks like a bell curve. That's why it's called a bell curve. Bell. Gauss, for the guy who invented, that's why it's sometimes called Gaussian curves. Normal, because it's normalized, right? When they talk about the norm, I'm not sure about the etymology of that, but I suspect it has to do with this mathematical idea. What's the average? What's the norm? Okay, there are these facts that come from probability, which you prove in higher level mathematics. That's way too advanced for this course. You just have to memorize these things, okay? If you notice once again that our experiment looks a little bit like the ideal, but with crooked imperfections, then the idea is that your sample relates somehow to that ideal bell curve. How does it relate? How does your K, your basically your experimental result, relate to the ideal mu? K, remember, is our average number. The probability that K is within sigma of mu happens 68%. The probability that K, your experiment, is within 2 sigma of mu is 95%, and the probability that K is within 3 sigma of mu is 99%. The basic idea is that the wider your fudge gets, the more likely your sample will fall within those bounds. Okay, you just have to memorize these facts, these 3 facts. It's basically 1 sigma is 68% of the time, 2 sigma is wider, that's 95% of the time, and 3 sigma is wider still, and that covers 99% of the cases. And let me show you how that works in terms of a diagram. So here's one way which this stuff has been applied in terms of IQ distribution, which is a hugely fraught thing. People say, oh, it's real, and it is partially real, but it's also massively controversial and not wholly real as well. I mean, what IQ measures in the test used is both biased and only partially measuring what it claims to measure. There's a whole debate about this. Books and books have been written about this. Let's leave it alone. Here's just one example I got here cited for that reason. So here's your bell curve, right? And here's your middle level intelligence for the whole world, let's say, right? And what you're saying is 68% of people fall within this range, okay? That's 1 sigma. 1 sigma is there to there. Just like with our previous sample when we calculated 50 and then sigma was 5, right? So plus or minus 5. In this case, you're saying 68% will fall within 1 sigma. So that means if 100 is your average IQ score, 68% will be between 85 and 150 on that scale. Okay? 2 sigma captures more. It's double this. So this length right here is 1 sigma going both ways. So you double that going both ways, you get 95% of your population. So 95% of your population falls within between 70 and 130. And then 3 sigma is 1, 2, 3, and then the other way, negative 1, 2, 3. It covers 99% of your population from on this side, which is barely functional, to that side, which is genius level. And then outside of that are your either 1, super geniuses, or 2, super ungeniuses. Yeah? Okay. For entertainment's sake, here's one way which stuff actually has been applied. They talk about the so-called science of beauty. Yes? Remember this guy? Wow, I love it. On the sample, he's a bit crooked. That's like our sample, right? On the right, you have average, average Caucasian, average Asian. And then what they do is they blend it. What they find in these so-called studies of the science of beauty is that symmetry matters. The more normal a face gets, the more average you get across various so-called races, what you find is the ideal of beauty for both male and female. And when they ask people which face is more beautiful, they found that the average of the average of the average ends up being the most beautiful. So the average is beautiful. The most normal is beautiful. That's a bit of a twist on things. But this normal, this average is different from what we think of as average. Pale, beautiful. Not for you. Moving on. A worked example. You're going to need this for the upcoming quiz, as well as future uses of this stuff. Suppose you're buying Christmas ornaments, whether it's Christmas season or not. UPS, let's suppose, advertises 90% will arrive unbroken, 10% will be damaged in some way. So it's binomial. Either it's basically binomial means two outcomes. It's either broken or not, right? So you can model it as a Bernoulli trial. You go crazy and you order 3,000. The expected number of unbroken ornaments should be P times N. 90% times P is the percentage, 90% times N, the number you order, 3,000. So you expect 2,700 to be unbroken. That's the mean, mu. You calculate now sigma. That's square root of 1 minus P times N, which equals that. So plus or minus 16. Here are how the three facts relate. So you take your 2,700 mu and you add 16. That's 1 sigma, and you minus 116. So 2,700 plus 16 is 2,716. Minus 16 is 2,684. And you're saying 68% of your, for an order of 3,000, the chances that you have the number of unbroken ones lying between this is 68% chance. Okay? 2 sigma is 2 times 16, 32. So 2732 on one side and 20 minus off from 2700, so 2668. You're saying the number that you get unbroken between that level is going to be 95% of the time. And then 99% of the time, you'll get between this number unbroken. Okay? If you get a number outside of this range, that's highly unusual. So you're saying that given these facts, 90% will arrive unbroken. 99% of the time, what that means is you're going to find the actual number of unbroken ornaments between these two numbers. That's your range of expected, what you could expect. Now, it might fall outside that range. You might say, oh, you get a shipment, and it isn't that 2,700 occur unbroken. You get, in fact, almost all of them broken. So that falls way outside the 99%. You might say, UPS has claimed that 90% will arrive unbroken. That's BS. But if they did this correctly and they're tracking their past records of these kinds of shipments, what that means is something very unusual happened in almost all other cases, 99% of the other cases. So that means if 1,000 people actually ordered Christmas ornaments, 999 of those, well, this is not totally accurate, but a lot of those people, again, the 99% refers to actual number of ornaments here. I'm cheating a little bit, but it still helps to tune your intuitions. You're saying 999 people were satisfied customers. There's only one person in that grouping, or 990 actually. 990, there's only 10 people in that grouping who got broken ornaments that were outside this. Either more were broken or less were broken. Yeah. Okay, that's it for this. To get a better sense how this works, I'll help you out with the quiz. Work that. That's good practice for the upcoming final. And it tests you in all these concepts. There's a lot here, but once you get the basics down, it's actually pretty straightforward.